28.
ECS reduced for launch.
Roger. 25.
Status check.
Go Atlas.
Go Centaur.
Go STP-3.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And we have liftoff of the United Launch Alliance Atlas V rocket with the STP-3 mission for the United States Space Force.
Vehicle has cleared the tower and is beginning the pitch over program. And the RD-180 is throttling down slightly as expected. Engine response looks good. And passing 20 seconds into flight, the PU system has gone to closed loop control. SRB chamber pressures continue to look nominal. RD-180 pump speed and fuel injector pressures continue to look good. Mach 1, Atlas V is now supersonic. Passing 45 seconds into flight, vehicle is now passing through max Q, maximum dynamic pressure. And the RD-180 is throttling back up as expected. Engine response looks good. Passing 1 minute into flight, the vehicle is now 9 miles in altitude, 7 miles downrange, traveling at 2,200 miles per hour. And the RD-180 is throttling down again as expected. Engine response looks good. Standing by for SRB burnout shortly. And just past a minute and a half into flight, we have burnout on all 5 SRBs. Burnout pressure signatures are looking good, and the RD-180 is being throttled back up as expected following SRB burnout. Standing by for jettison shortly. And we have good indication of jettison of all 5 SRBs, and the vehicle has gone to closed loop Q alpha limited steering following SRB jettison. Body rates are looking good. And coming up on 2.5 minutes into flight, a little over 2 minutes remaining in the boost phase of flight. And the RD-180 is now throttling to maintain a constant 2.5 G acceleration limit. Engine response and vehicle response looks good. And the Centaur reaction control system is now pressurizing to flight levels. Passing 3 minutes into flight, the RD-180 pump speeds and fuel injector pressures continue to look good. The vehicle body rates look very good for this phase in flight. And the vehicle is now 65 miles in altitude, 150 miles downrange, traveling at 7,800 miles per hour. Standing by for payload fairing jettison shortly. And we have good indication of payload fairing jettison. And we have Centaur forward load reactor deck jettison. And the RD-180 is throttling back up as expected. Engine response looks good. And the RD-180 is now throttling to maintain a constant 5G acceleration limit. Engine response continues to look good. And Centaur has begun the boost phase chill down portion of flight to thermally condition the RL-10 for operation. And we've had BECO, booster engine cutoff, and we've had successful stage separation, and saying pre-start on the RL-10. And we've had ignition for the first burn. This will be the first of 3 Centaur burns for today's mission and will last a little under 6 minutes. The RL-10 startup parameters are looking good, and seeing the body rates close out nicely.
This is Atlas Mission Control at T plus 5 minutes and 21 seconds. You just heard our flight commentator, Jesse Gonzalez, confirm the successful completion of the early phase of today's flight, and all systems continue to operate nominally. Our next event, Centaur main engine cutoff, will occur in approximately 5 minutes. I'm now joined by Emma Coates. She's RUOG's Payload Fairing Program Manager. Thank you so much for being here with us today.
Yes, thanks so much for having me. It's such an accomplishment to be here and to witness the jettison of our first payload fairing, our first out-of-autoclave payload fairing.
Yes, it's been great. I mean, it's a huge accomplishment for the team, and we're going to talk a lot about what that means, out-of-autoclave manufacturing. But as you know, you guys have been producing payload fairings for us for quite some time, but this is the first one that we've flown using the out-of-autoclave process. Can you explain to us a little bit about what that means?
Yeah, so normally when we talk in autoclave or out of autoclave, we're talking about the curing or the baking process that goes into creating creating a payload fairing or a composite structure. The autoclave itself is actually the container that is performing this curing or baking process.
Great. So in autoclave versus out of autoclave, what are some of the benefits of the out of autoclave process?
So a few of the benefits of the out of autoclave process is actually the fact that we're able to be a little bit lighter in weight. We
like that.
Right. So we're saving time and cost and everything also because we don't have to have that same internal pressure requirement that's used in the in autoclave process. We're able to lay up an entire half shell of a fairing with just one oven cure cycle, which saves a ton of time.
That's great. I mean, a lot of efficiencies there. We're all about efficiencies and making things better going forward. So what a huge accomplishment and what a fantastic process you just kind of went through for us. So as you know, you have a production facility that also shares our ULA Decatur production facility. This was the first fairing that was actually produced there and flown now. Can you tell us a little bit about the partnership between RUOG and ULA?
Gotcha. Yeah, so we have many years that, as you mentioned before, we've got a ton of years of partnership with ULA, both on our RUOG Switzerland side and our RUOG US side. But with this being the first one out of Decatur, this actually allowed us to be super close to you guys, sharing that wall essentially. So we were actually able to issue, I guess, better delivery, I guess would be the time frame, or be the thing, but we were able to have better delivery times, save on logistics, which is, again, saving on a ton of costs.
We love the efficiency. Again, we're talking about efficiencies here.
Yeah.
I mean, the one thing that's been great, we obviously talked about process efficiencies, which was awesome, but I mean, you're talking about process flow efficiencies as well. We literally share a wall with our two facilities, so you can't get more efficient than that.
Yeah.
All right, so something near and dear to my heart. I've been lucky enough to work with you on the Vulcan development program for a long time now. As our viewers may not know, you're actually producing the Vulcan payload fairing for us as well. So can you give us a little bit of a status on where we're at with that development program?
Sure. So we're actually nearing the completion of our qualification process for that. And of course, we're gathering all of our lessons learned from this launch and any of the other payload fairings we're building as well. That way we can make sure that Vulcan is also a success as well.
Right, and it's been so great to watch that qualification testing that we've been doing at Marshall Space Flight Center. So excited to see that come to completion and fruition and things like that. So it's been really great, you know, learning more about the first out of autoclave fairing. I'm so happy to have you here. Emma, thank you for joining us, and I hope you have a good rest of your day. And again, congratulations.
Thanks so much for having me.
All right. Okay, let's get back to the mission. We're coming up on the end of the first of 3 Centaur engine burns. Our next event is the first Centaur main engine cutoff for MECO 1. Once again, here's Jesse Gonzalez.
And standing by for MECO 1 shortly. And seeing PU go to open loop control in preparation for MECO. And we have MECO. Engine cutoff pressure signatures look good. Centaur will coast for approximately 1 hour prior to the next burn. And the RCS system is now commanding 100% settling to settle propellants in the tank following the burn.
This is Atlas Mission Control at T plus 11 minutes and 30 seconds. Jesse Gonzalez just reported the successful completion of the first of 3 Centaur engine burns. Centaur is now in coasting over the Atlantic Ocean west of Africa, but we still have a long way to go. STPSat-6 is scheduled to separate from Centaur into geosynchronous orbit in just about 6 hours and 20 minutes, followed by 40 minutes later by separation of LDPE-1. To tell us more about the spacecraft, I am now joined by the STPSat-6 Program Director, Ray Crow. Ray, thank you so much for being here today.
Oh, I'm absolutely delighted to be here today. It is a great day for our nation.
It is a great day for our nation.
Absolutely fantastic.
Very exciting. Finally got off the ground,
Yeah.
which was great. But thank you for taking a couple of minutes off console to be here with us today.
My pleasure.
I'm excited to learn more about STPSat-6. So to get us started into the questions, why don't you tell us a little bit more about Northrop Grumman's role in this mission?
I'll describe Northrop Grumman's role in this mission, but I'll give you a bonus item.
Oh, great.
I just got a note from our engineers here on site, and we are receiving spacecraft telemetry as expected. Absolutely
Oh, that's
fantastic.
amazing. I love the up-to-date information.
So we have a very significant role in this mission. I'll start with the Northrop Grumman contribution from the top of the rocket to the bottom of
Great.
the rocket. There are 2 spacecraft. The top spacecraft is STPSat-6. STPSat-6's mission is to explore science that will inform a generation of spacecraft design and mission design. Northrop Grumman's role for STPSat-6: design, development, test, integration of the payloads, and support of the mission over a 10-year period of time.
That's quite a life cycle.
It's a fantastic life cycle, but you contrast that to this program has been under motion for the last 7 years. So this moment.
Long day coming.
Punctuation point between 7 years of development and the first hours of 10 years of operation. So we are very excited about that. As we move down the stack, LDPE number 1. LDPE stands for Long Duration Propulsive EELV.
Very good.
An acronym
Yes.
within an acronym.
Love those.
So think about LDPE number 1. It is a ring. However, it is an extremely smart ring. It is a spacecraft, and you can affix payloads to that spacecraft. There are so many advanced scientific payloads that are sitting on shelves right now, and for lack of financial resources, we cannot get those in space. Enter LDPE number 1 and the platform ESPISTAR produced by Northrop Grumman. So we have an inexpensive and an easy way to integrate payloads that represent the forefront of technology, a way to reduce risk, to test payloads in space early, and even better than that, the opportunity for residual operational capability. We continue our walk down the vehicle this morning, and we have had, it is a pride point for us, and the pride point is the relationship with Atlas over a 3-decade, more than 30-year period of time.
A long heritage there.
Extremely long heritage. So everyone, of course, saw those magnificent GEM engines. Those are produced by Northrop Grumman.
Yes.
We also produce some composite structures for the Atlas as well. So a great deal of Northrop Grumman content, and certainly a great deal of employee pride when we see an event like this and prepare for 10 years of operation.
It's quite an integrated team effort, but it's really amazing to see all of the aspects that Northrop Grumman has been involved in over this long period of time. So again, congratulations on us finally getting here today. So let's take a look now at our payload. What makes STP-SAT-6 unique?
Well, we'll start with a very capable and a very prestigious client, the U.S. Space Force. We work with the Space Test Program located at Kirtland Air Force Base. Their leadership in this has been absolutely remarkable. And then as we work through the rest of the mission, and so STP-SAT-6 has set all sorts of records on our Dulles campus. One for today is this is our 200th spacecraft.
Congratulations!
From our Dulles campus.
It's exciting.
And we'll say LEPE was 201. But,
okay, that's fair. That's fair.
STP-SAT-6 is number 200.
Okay.
We have set perhaps 25 records for spacecraft that have moved through our campus. It is our first rad-hard bus. It is a redundant bus. It is designed for a 10-year life, and it has been just an absolute delight to develop and to build.
I mean, that's great. It's truly amazing to hear about all of the activities that went in today and how unique the spacecraft is. So in terms of the actual mission today, can you give us a little bit more information about the mission milestones we can expect to see?
Absolutely. So we'll start with 20 minutes before we were launched today. We went to internal power, but internal power for us means we are on our batteries, but the Centaur carries batteries as well.
Correct.
And that assures us that when we are released, that we will have, let us say, a full head of steam. Our batteries will be fully charged. So we will be attached to the Centaur for another 6.5 hours.
It's a very long mission today.
It is actually the length of this mission is a record.
Another record.
Another record.
Yeah, for both of us actually.
Absolutely.
Yeah.
So also great there too.
Mm-hmm.
So after 6.5 hours, we will pop off the vehicle. Gently pop off the vehicle.
We like a gentle ride. Delivery to the right place.
Delivery to the right place. And so on this 6.5 ascent, we are in a mode called all safe, which means we cannot accidentally deploy any of our mechanical appendages. So we will pop off the rocket. At that time, thrusters will be enabled, wheels will be enabled, our solar array will deploy, and we will find the sun. And then the ground segment will acquire us. At that point, that's when it's thumbs up and the launch has been completely successful when we are delivered on orbit. Once on orbit, we will undergo a test regime 66 days, plus or minus 66 days.
A little bit longer.
And then we will transition to government operation, and that puts us in a role where we will support these operations for a decade.
Oh, great. It's a really long time. I mean, we're talking about long times to get us to orbit. Now we're talking long time in orbit. I mean, it's truly great to hear all about the heritage, the history, and our mission today. So before we let you go, is there anything else you'd like to add?
Well, absolutely.
Always, yes.
Always, absolutely. So here's what I would add today. I will finish today with the words that we use when we start every major meeting with our stakeholders. And when I say stakeholders, and when I use the word team, team goes far beyond the boundaries of the Northrop Grumman employee family. It includes the Space Force, NNSA, NASA, ULA, and a broad community of stakeholders. And the words that we use are this: if you're willing to work as a team, anything is possible. That's my message today.
Yeah, I mean, we all know how complicated everything is with this entire process. So quite a collaborative effort, and congratulations again today. I have certainly appreciated all of the information you've provided to us. I know our viewers have enjoyed it as well. I can certainly feel your enthusiasm. So I know everybody's really appreciated that. But certainly, thank you for spending some time with me today and letting us know a little bit more about your role in the mission.
Thank you for the opportunity.
Great.
I appreciate it very much.
Thank you so much.
Have a great day.
All right. Before I toss today's live coverage back to our NASA partners, where you'll hear more about the laser communication relay demonstration, I'd like to thank Jesse Gonzalez for his participation in today's show, as well as Brian Sizik from the Space Launch Delta 45 weather. You can stay updated on today's long ascent to geosynchronous orbit with ULA's live blog at ulalaunch.com, or join the conversation on Twitter and Facebook. I'm Andrea Lenhoff. Thanks for joining me bright and early today. Before we hand you back to NASA coverage, let's take one more look at the liftoff from today at 5:19 a.m. Eastern. Have a good rest of your day. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And we have liftoff of the United Launch Alliance Atlas V rocket with the STP-3 mission for the United States Space Force.
The vehicle has cleared the tower and is beginning the pitch over program. And the RD-180 is throttling down slightly as expected. Engine response looks good. And passing 20 seconds into flight, the PU system has gone to closed loop control. SRB chamber pressures continue to look nominal. RD-180 pumps.
If you're just joining us, welcome to NASA's live coverage of the Laser Communications Relay Demonstration, or LCRD. It launched about 20 minutes ago from Cape Canaveral Space Force Station as part of the Space Test Program 3 mission. LCRD will demonstrate the unique capabilities of laser, also known as optical communications, versus the radio systems NASA uses now. And here with me this morning is Jeff Sheehy. He's the Chief Engineer for NASA's Space Technology Mission Directorate. Jeff, wasn't that a beautiful launch?
Oh, they're always amazing. I mean, right out there, the launch, the bright flash, and then you wait a few seconds and you hear that sound. It kind of beats against your chest. I've seen a number of launches now, and they never get old. Yeah, definitely worth the wait this morning. And so talk to me about, LCRD, again, is on its way now, but there's still a lot we need to monitor, right? Yeah, the spacecraft is going to be delivered to near its final orbital home in about 6 hours and 10 minutes from now. It'll be dropped off from the upper stage of the launch vehicle. And then it'll maneuver into place over the course of a couple of weeks. During those couple of weeks, the Space Force will be checking out their spacecraft. The spacecraft is more than just a host platform in terms of a place to mount all the LCRD stuff, but LCRD is going to rely on spacecraft systems to be working. So they'll bring up the spacecraft, check it out, make sure everything's working okay. Yeah. And then when we know, about 2.5 weeks from now, when the spacecraft is in its proper orbit, when the spacecraft has all been checked out, we'll be able to turn on the LCRD payload. Yeah, that's really exciting. And then when do you say, hey, this mission was a success? Is there a threshold we need to cross? There's a number of objectives that we have for the mission. All of the technology demonstrations that we do, we write formal requirements, and we have a set of mission objectives. And this one's no different. We've got objectives that will demonstrate the capability of transmitting data at high data rates from the ground to the spacecraft, from the spacecraft to the ground. Ultimately, there'll be other assets in space on the ISS, on the Orion capsule. We'll communicate between those and relay that data to the ground. The R in LCRD, the relay part, is really an important aspect of the demonstration here. It's not just about being able to send data from a spacecraft to ground, but relay that data to between other assets in space. So when we accomplish that, we'll basically show that, hey, it works great. That's what we're trying to do. We're trying to demonstrate how well does this work anyway. And so when we demonstrate that it works well, then we'll try out different operational scenarios. What we want to do is demonstrate the capability to a point where a mission planner could say, hey, that's a technology that I can really use to benefit my mission. So we'll try out different operational scenarios. We're going to be taking a lot of data on how well does the laser penetrate through the atmosphere, how well do we receive the data at these ground stations in California and Hawaii. There'll be some atmospheric interference. We have adaptive optics in the ground station to be able to correct for that. So with this launch, it just means more work for you guys. Yeah, we were just talking to the program manager before we came on, and he said, yeah, this is checking one thing off, but now the real work starts.
Right, but it's exciting work, and I'm so glad you guys got to launch today, and yeah, we'll just see when the experiments start in March. So thank you, Jeff.
You're welcome.
Thank you so much. And LCRD will be NASA's first two-way end-to-end optical relay because it can both send and receive data at once. Check out this video for why that is so significant.
LCRD will relay sample data, like glimpses of planetary surfaces or satellite health down to Earth over infrared lasers. Historically, NASA has used radio waves to communicate. When we landed on the moon in 1969, Neil Armstrong's first words came across radio waves.
It's one small step for man, one giant leap for mankind.
When we go back to the moon, we're going to stay longer and explore more. With so many new and exciting things happening on the moon, missions will need a better way to talk with Earth. And that's where lasers come in. LCRD will demo the vast capability of laser communications. This includes transmitting 10 to 100 times more information to Earth than is possible using radio systems, meaning missions can send more detailed photos, videos, and data. When LCRD reaches its destination, it will spend 2 years conducting experiments that will be developed by NASA and our friends in industry and academia. LCRD's first orbiting experimental user will be the International Space Station. Astronauts live and work there, conducting research about life in space, microgravity, biology, and more. Using lasers, the station will be able to relay more experimental data to scientists on Earth. Laser systems are great for missions like the space station because they weigh less, are smaller, and use less power than radio systems. A smaller size means more room for science instruments. Less weight means a less expensive launch. Less power means less drain on the spacecraft's batteries. LCRD and the space station will work together and demonstrate laser communications near Earth. This will help prove laser systems are an option for future expeditions back to the moon and then on to Mars.
Thanks again for joining us for this live launch coverage of LCRD. Again, it will orbit about 22,000 miles above the Earth's surface while it conducts 2 years worth of experiments. You can follow all the updates at nasa.gov/lasercoms. You can see it right there on the bottom of your screen. And you can never get enough video of a beautiful launch, so let's close out the show with another replay. Have a wonderful day, everyone.
T-minus 10. 9, 8, 7, 6, 5, 4, 3, 2, 1. And we have liftoff of the United Launch Alliance Atlas V rocket with the STP-3 mission for the United States Space Force.
The vehicle has cleared the tower and is beginning the pitch over program. And the RD-180 is throttling down slightly as expected. Engine response looks good. And passing 20 seconds into flight, the PU system has gone to closed-loop control. SRB chamber pressures continue to look nominal. RD-180 pump speed and fuel injector pressures continue to